Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel, and it also helps us reach others in need of assistance with these topics. So what we're going to be going over in this video is that we're going to be looking at statics, and we're going to be looking at the method of joints being used to solve trusses, and this will be our first part in this series. So we have this truss shown here on the left, and we are tasked with determining each member force and determining if it's in tension or compression. And we're going to be using the method of joints to solve the truss. So there are two methods that you can use to solve trusses. One is the method of joints. The other is the method of sections. So the method of sections is where the truss is a little bit harder, or if you want to find a single member. Method of joints is where you look at a single joint one at a time, isolating that joint and only concerning ourselves with what's being applied to that joint, that being member forces or reactions or applied forces. When we are looking at or using the method of joints to look at a single joint in a truss, we do not care what else is happening for that particular joint. So the method of joints is where you would look at one joint at a time, finish all the members that you can at that joint, and then go to another joint, repeat the process, look at all the members acting on that joint, complete as much as you can, determining the forces in those members, and then just going to another joint and to another joint, and then finally finishing it off. So that's the method of joints. And the method of joints, there are two different ways that you can do the method of joints. One is a little bit longer, one is a little bit shorter. One of the methods is where you actually, let's say you want to look at joint A, where you would actually draw out your joint and the members connecting in and the forces being applied. And then you would sum forces in the X and Y direction for the unknown member forces here. Every horizontal member will just have a single horizontal force. Every vertical member, which we don't have any for this truss, but they would look like that, have a one vertical force, and a diagonal member, everything at a slant, will have an X and Y component force. So that would be one way that you could use the method of joints. The other way is a little bit faster, and this way you would just write on the truss itself instead of redrawing little joints everywhere. So the second part is the faster one, where you just work from joint to joint on the truss, putting the member forces on the truss. And that's the one that we're going to utilize because it is much faster. You just need a large picture of your truss in order to do this, or you need to redraw your truss in order to make room for putting the forces on those members. All right. So the first thing you want to do when analyzing trusses, which means finding the internal forces that are acting inside of each member, you have to start with your reactions. You must determine your reactions first. So we have a roller down here at E. So I'm just going to say this is E sub Y, assume it upward. We have a pin reaction here, which I'm just going to assume C sub Y is upward. And I'm not going to have an X reaction here because there are no X forces acting on this truss. So C sub X would automatically be 0. So I'm just going to sum forces at point C in order to get my reaction E sub Y. I'm going to go through the reaction a little bit faster because this is more of a truss than a reactions problem. We do have other videos on the channel that look at reaction problems. So we would have our 200 pounds times a perpendicular distance of 24 feet. It would be positive rotation plus the 1,000 pounds times the 12 feet positive rotation minus E sub Y times 6 for clockwise rotation, all that equal to 0. E sub Y would pop out to be 10,000 pounds in that upward direction. So this down here is 10,000 pounds. Then you could sum forces in the Y direction to get C sub Y. And C sub Y, if you do it the way it's shown here, is up, you get minus 7,000 pounds, which just means I assume the wrong direction. So it's actually 7,000 going downward. So right here at joint C, we have 7,000 pounds in the downward direction. And typically a good rule of thumb before you actually start your truss problem, if you're not given the reactions and you have to find them, just do the check before you move on. So since we sum forces at C, just some moments at C, since we did C first, just do E. Some moments about E to make sure everything is equal to 0 before you move on. Because if you have the wrong reactions, your truss is going to be wrong. All right. So utilizing the method of joints. This is where you get to just pick a joint that you want to start with. Now, if you pick a wrong joint to start with, no big deal. that just means you can't really solve much at that joint. Anytime you get stuck with a joint, just go to a different joint and see if you can solve anything. So with this particular one, I'm going to start with joint C. So starting with joint C, what I have is that I'm going to isolate joint C out, and I'm only going to look at what's being applied at joint C. Well, I have this horizontal member BC, this diagonal member EC, and every time I have a diagonal member, I am going to have, give me my pen back, please. Not the eraser, thank you. I am going to have a vertical and horizontal force because it is a diagonal, so it's going to have a component in the X and component in the Y. So I have two member forces I have to determine, technically three, because I have BCX, ECX, and ECY. So looking at joint C, if I were to sum forces in the horizontal direction, I would have this unknown force for BC and this unknown horizontal for EC. Well, can't use that for two unknowns. But look at this. I have 7,000 pounds in the downward direction at C. This diagonal member has to apply a vertical force here at joint C. Well, this is the only other vertical force that is coming into joint C, or the only other horizontal or vertical member. Well, that means that we have 7,000 pounds downward. In order to cancel with the 7,000 pounds downward at joint C, this has to be 7,000 pounds for that vertical portion, and it has to be going upward relative to joint C. Well, what this means is that whenever you have a diagonal and one of your components that you have found is pointing in a certain direction, the other component for that diagonal has to match that general direction. So for example, this is member EC. I just found that the vertical component relative to joint C has to be going upwards. Well, forces for trusses have to align with the direction of that member. Since it is going diagonal, you either have two choices of up and to the right or down and to the left. The internal force, since it is an axial force, has to be going parallel to that member. So since this one is going up, it cannot be that one. It has to be going up and to the right. And since it's going up and to the right, that dictates which way the X is going for the component. So essentially, this force is going like this, up and to the right relative to joint C. Well, how do I find that X force for that diagonal? Anytime you have one of the components for a diagonal, you can find the other one. Since it is going to be an axial force, meaning that these two components have to go in the same direction as the diagonal, well, it's going to be relative to the slope of that diagonal via this ratio. So you would have your X force over your Y force is equal to the X dimension over the Y dimension. So the X force would be your horizontal component. The Y force would be your vertical component. XD would be your horizontal distance that diagonal member runs. And your Y dimension would be the vertical distance that diagonal member runs. So for EC here, we would have our X force, which is unknown at this time, over our Y force, which is 7,000 pounds, is equal to our X dimension for that diagonal, which it runs 6 feet, over the vertical dimension for that diagonal, which is 8 feet. The slopes have to match. So we can just rearrange for our X force here, which would just be 7,000 pounds times 6 divided by 8, and that would give me 5,250 pounds. And that 5,000 or 5,250 would be acting to the right because of this arrow direction. Alrighty, so since I have both X and Y components, I can just find my overall resultant for this diagonal member. You would just take 7,000 pounds squared plus 5,250 squared, square root it, and you end up with 8,750 pounds for that member. All right, now let's finish off joint C. Well, we have the vertical completely in equilibrium here at joint C. 7,000 pounds down, 7,000 pounds in the upward direction. Well, we have 5,250 to the right because this arrow is up and to the right. Well, there is no other X force applied at joint C. The only other thing that can resist this 5250 to the right is BC. So relative to joint C, it has to be pulling to the left 5250 pounds to cancel with that horizontal component of the diagonal EC. So that is joint C completely solved out. Everything is in equilibrium with joint C right now. We have 7,000 pounds down, 7,000 up, 5250 right, 5250 left. And that is what you're going to do with the method of joints at every single joint. It just gets really repetitive. Okay, so before moving on to our next joint, what we're going to do is what's called completing the member. So the only thing that you have to do is that if you know the arrow direction relative to a joint for one end of the member, the opposite end of the member is going to have the arrow direction in the opposite direction. So opposite end, opposite arrow direction. So since it is pulling on joint C, this member also has to be pulling on joint B. Likewise, for this diagonal, it is pushing up and to the right at C. Well, it's going to have to be pushing down and to the left at E. Opposite end, opposite arrow direction. And what this signifies is that whenever you have a member that looks like this, can be diagonal, vertical, whatever, when the arrows are pulling on your joints, just think about when you go over equilibrium problems. When you have an arrow pulling on a joint, that's tension. Anytime you have a member and you are pushing on a joint, pushing is compression. And the way you can think about this is that these joints are trying to push in on this member. They're trying to collapse it. The member has to push back to keep itself in equilibrium because it's being compressed. Same thing on this one. The joints are trying to move away. The member has to pull back to keep itself in equilibrium because it's in tension. So typically with trusses, what you would do with these little arrows is you would write tension or compression with capital T or capital C. Since this one is pulling on joint C, it is pulling on joint B, so that is tension. This one is compressing both ends, so that is compression. It is pushing on both joints. And that would be your completed member for BC and EC. Alrighty, so we completed C. Now we just move on to a different joint. And with the method of joints, there really is no one right path that you can take. It's not saying like there's one next joint that is correct. It just depends on where you want to go. So let's go ahead and let's try joint E down here. So once again, we are going to isolate joint E, and we're only going to look at things that are attached to joint E or acting on joint E. Well, we have our reaction of 10,000 pounds upward at joint E. We have the 7,000 pounds, 5250 in the X and Y acting at joint E. I have this diagonal member here that is going to have an X and Y, and this horizontal member here, DE, that's acting at joint E. So looking at what's unknown and what's known at joint E, I have one vertical and two horizontal forces that I need to find. Whenever you have the one that's unknown, find that one first. So for BE, it has to be in equilibrium with everything that's acting in the vertical direction. Well, we have 10,000 pounds upward. We have 7,000 pounds that is being contributed from this arrow, which is down and to the left. Since it is down and to the left, the 7,000 pounds is going to be going downward. Well, I need an additional 3,000 to go downward with the 7,000 to cancel with the 10,000. So I need an additional 3,000 pounds here, and it has to be going in that downward direction, so down and to the right, to cancel with the 10,000. So just like before, if you have one member of your diagonal, you can get the other one. Well, just use your ratio over here of the X force over the Y force is equal to the X dimension over the Y dimension. So in this case, we're looking for the X force. Our Y force would be 3,000. The X dimension, once again, is 6 feet, and our height, once again, is 8 feet. So once you use that ratio, this horizontal comes out to be 2,250 pounds. And since the 3,000 has to be going downward, the 2,250 is already dictated that it is going to the right. Because this member right here only has two options of up and to the left or down and to the right. Alrighty. So now I only have one horizontal unknown, DE, at joint E. Well, I have 5250 right here acting to the left because the arrow is down and to the left. I have 2250 acting to the right because this is down and to the right. Well, I need an additional 3000 here acting to the right to help with the 2250 to cancel the total of 5250 acting to the left. Alrighty, so now we have joint E completely in equilibrium. So let's complete the members here by drawing on the arrows. Well, this one is to the right. It is pushing on joint E. So it's got to be going opposite direction, which is to the left, and push on joint D. Same thing for the diagonal. It is pushing on joint E. It is down and to the right. So it must be going up and to the left, opposite end, opposite arrow, pushing on joint B. Whenever I say opposite end, opposite arrow, it just means the direction. It still has to either be pulling at both ends or pushing at both ends. You cannot have a member that looks like this, where the arrows are going in the same direction. It does not work, cannot happen. So this DE is pushing on each end, so that would be compression. This member right here, which is 3,000 pounds, 2,250 in each component, well, if you were to find out the total there, it'd just be 3,000 squared plus this squared rooted, and you end up with 3,750 pounds. And since it's pushing on each end, that is compression. Alrighty, so now we have two joints done, and we're gathering up a lot of members here. So where to next? Well, let's see, if you try to go to point B, you could do it. It's just a little bit harder. If you go to joint D, there's too many unknowns there. You can't do it because, well, look at this. We have horizontal, vertical at joint D, too many unknowns. Joint B, you could do it. But isn't joint A easier? If we look at joint A, we have this horizontal right here, horizontal and vertical. A whole lot less forces to deal with because we just have the 2,000 pounds going downward. So let's jump over to joint A. As I said with method of joints, you can just jump around. Does not matter what the order is. So jumping over to joint A, we have 2,000 pounds downward. That is it. Because remember, we don't care what's happening anywhere else, just what's happening at joint A. So since we have 2,000 pounds going downward, I need 2,000 pounds upward right here in order to cancel with that, because this is the only vertical that can. And it has to be going up and to the left because the only other option is down and to the right, which can't happen because it has to cancel with that 2,000 going downward. So once again, since you have one of your diagonal components, you can get the other via this equation right here. And when you do so, you get 1,500 pounds here. And since the 2,000 has to be going upward, this 1,500 has to be going to the left at joint A. Well, this is the only other horizontal there that can cancel with the 1,500. Since this 1,500 is going to the left, this one has to be going to the right at joint A, and it has to be going 1,500 pounds. So let's complete the members here. Since we are pulling at joint A, we have to be pulling at joint B to the right here, opposite over here to the left. We are pushing up here at joint A, we have to be pushing down here at joint B, up and to the left, opposite end, down and to the right. So let's find the resultant force through AD here, the actual force inside that member, the axial force. So it'd be 2,500 pounds. And since both members or arrows are pushing, that is compression. Both arrows are pulling up here, so that is tension. So we only have one more member to go, and that is D to B. Well, you can either look at joint D and solve it, or you can look at joint B and solve it. It does not matter. Well, if you go to joint D, it's a little bit easier because you have less forces to deal with. So looking at joint D, we have 3,000 pounds acting to the left. I have 1,500 pounds acting to the right here from this arrow at D. So what do I need to cancel with this 3,000? I need an additional 1,500 in the horizontal here from this member, and that's going to have to be going to the right. So that means it's going to be going up and to the right. So as before, once you find one of your components, you can get the other via your ratio. So once you do so, you get 2,000 pounds here for the vertical. And does that cancel at joint D? Well, this is horizontal, don't count it. Horizontal, don't count it. Horizontal, don't count it. We have 2,000 pounds here going downward, 2,000 pounds going upward at joint D. Yeah, joint D is in equilibrium, so we don't have to worry about it. All right, so this resultant force will be 2,000, 1,500, each of those squared, added up, and you get 2,500. Let's complete the arrow at the opposite end. It is pulling, so it must be pulling. And that means we are in tension since we are pulling. All right. So when you get to the end of your truss, which this is the end because we have all our tension compression forces, we have all our forces written out. And this was the fast way if you just write on the truss. As you can see, you better leave yourself plenty of room because it can get kind of filled in throughout there. So typically with trusses, what's going to happen is you're going to get one member or one joint that you did not use. And it'll be your final joint that you just go over to. And the final joint that we did not use here was joint B. So looking at joint B, what do we have going on here? Let's make sure everything's in equilibrium, because if joint B is in equilibrium, we're good. We did it correctly. If it's not in equilibrium, we did something wrong. So let me erase a few things here if the program wants to cooperate. All right, so looking at joint B, let's take our horizontal forces first. And everything has to cancel and be in equilibrium here. We'll take to the right as positive. So we have 1500 going left here at joint B. It's pulling to the left of joint B. So that would be minus 1500 plus 5250 here pulling to the right of B. And then what do I have going over here? I have 2250. This is up and to the left. So that'd be minus 2250. And then also over here, what else do I have? I have 2000 or 1500 pulling to the left as well. So minus off 1500. Well, what does that equal out? That equals out to 0 because that's minus 3000. And then if you add 2250 to the minus 3000, also in the negative, you get 5250. So the X is in equilibrium. Well, what about the vertical direction? Well, the vertical direction, I have the 3000 going upward, 2000 going downward at B, and then the 1000 pounds going downward. So the 2000 downward plus the 1000 downward will cancel with the 3000 going upward. So this truss is good. We solved everything correctly because our final joint is in equilibrium. If your final joint is not in equilibrium, you did something wrong somewhere. Now, as with most problems, it does not necessarily have to equal 0. It may be very, very, very close to 0 just due to rounding. So that's how you would use the method of joints to solve that truss. And that is the method of just writing on the truss and working along as you go. So I hope this video is helpful. And if you want to see more problem solved this Friday, please check out the other videos on the channel. As this was our first part in the truss series of method of joints, we will be putting more of these up on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel. Thank you for watching, and I hope you have a fantastic day.